Have you ever stopped to think about what makes steel so incredibly strong?
Yeah, but sometimes surprisingly flexible too, or tough.
Exactly. Think about bridges, spanning vast rivers or pipelines carrying vital
Even the
resources.
frame of your car.
Right. These aren't just solid chunks of metal.
No, they're really masterpieces of material science,
Yeah.
designed to be robust, reliable, under incredible stress.
Okay, let's unpack this a bit then. Today, we're going on a deep dive into something really foundational,
Hmm.
foundational to engineering, material science, the fascinating world of heat treatment for steel.
Yeah, it's far more than just heating something up, isn't it?
Oh, absolutely. It's a precise art and science.
Mm.
It fundamentally dictates how strong, how tough, or even how, well, ductile steel becomes, how much it can bend.
What's truly fascinating here, I think, is that the entire journey of steel, from raw material right through to the finished product,
Yeah.
it's profoundly shaped by these thermal processes. We'll be looking at how steel's supply condition, that's basically its inherent properties, is defined by its specific heat treatment.
And why this is so critical, especially when you get into welding.
Absolutely crucial, yes. When welding's involved.
So, our mission for this deep dive is really to extract the most important nuggets of knowledge from our sources about these, well, pretty complex processes, so
Yeah.
you'll understand not just what these heat treatments are.
But why they matter so much.
Exactly, for everything from, say, a bridge's resilience to a critical pipe joint.
And, how these unseen processes ensure the safety of our world.
We'll try and cover everything, from how steel plates get their initial properties, setting their sort of starting state,
Right.
to the critical post-weld treatments that ensure the integrity of a finished structure.
And hopefully by the end, you'll grasp the terminology, the principles.
Yeah.
What keeps our world safely constructed.
Why every degree and every minute in that furnace truly counts.
Precise.
So let's start right at the beginning. When you acquire a piece of steel for a project, it doesn't just come as like a generic metal block.
No, not at all.
It arrives with a material test certificate, and that spells out its supply condition.
Think of it as the steel's birth certificate, really.
Yeah, that's a good way to put it, detailing exactly how it was initially treated and what properties it now possesses.
And this immediately brings up a vital point. Why do people like welding inspectors, or, well, anyone involved in fabricating with steel need to be so familiar with this birth certificate?
Why? Why is it important?
Because they rely on these certificates constantly.
Hmm.
They might even be delegated tasks of monitoring crucial post-welding heat treatments.
Okay.
Meticulously checking records, ensuring everything aligns with the material's intended use, the design specs.
So it's about matching the right steel to the right job right from day one.
Exactly. It's foundational.
And it's genuinely fascinating how just by applying different initial heat treatments, fundamentally the same steel, the same chemistry, can be given such wildly different properties, completely shaping its ultimate purpose.
Mm-hmm.
So let's delve into some of these common starting states for weldable steels. These are the treatments done before welding, setting the stage, you could say.
Okay, kicking things off.
First up, we have steel delivered in an as-rolled or hot-rolled, or sometimes called hot-finished condition.
Okay.
Imagine rolling out a sheet of dough for a pie crust and just letting it cool naturally on the counter.
Right, simple enough.
That's essentially what as-rolled steel is. It's hot-rolled to its final size, then simply air-cooled.
But, and this is the key part, because that final cooling temperature isn't precisely controlled.
It's a bit like baking without a consistent oven temp.
Exactly. The final properties, like its strength or how tough it is, they aren't always optimally developed or perfectly consistent.
Okay.
So this foundational process is typically applied to relatively thin, lower-strength carbon steels.
So, basic stuff.
It's functional, yeah.
Yeah.
But as you can imagine, it's not the choice when you need precision-engineered properties or, the highest performance.
The internal structure isn't optimized.
Right. The microstructure, the internal arrangement of the atoms, can be a bit coarse and uneven.
Now, this is where things get considerably more sophisticated. Thermomechanical controlled processing.
TMCP.
Or TMCP for short, yeah. Sometimes called control-rolled or thermomechanically rolled steel.
Okay, so moving up a level here.
Definitely. If as rolled was like letting go cool on the counter, TMCP is like a Michelin-starred chef baking that dough.
Huh.
Precise temperatures, specific times, meticulously controlling every variable.
So what does that involve?
It involves carefully orchestrated thickness reductions during the hot rolling,
Mm-hmm.
all within rigorously controlled temperature ranges, and even the final rolling temperature is precisely managed, all to get the exact properties they want.
And if we connect this to the bigger picture, TMCP is a real game changer.
How so?
Well, it's applied to relatively thin, high-strength, low-alloy steels, HSLA steels,
Okay.
and even specialized cryogenic steels, designed for good toughness at incredibly low temperatures.
Wow.
The insight here is that you're achieving specific high-performance properties not primarily through adding lots of expensive alloying elements,
Oh, right.
but through extreme precision in the mechanical and thermal processing itself. You're refining the internal structure, the grain size, to an incredibly fine level.
Very clever. Okay, let's move on to normalized steel.
Normalized, okay.
Imagine heating steel to a very specific high temperature around 900 degrees Celsius.
Okay, hot.
Yeah, where its internal structure completely transforms into what's known as austenite.
That's a specific atomic arrangement, right? High temperature phase.
Exactly.
Yeah.
Then, instead of, say, rapid cooling, you just let it cool in still air.
Air cooling, so slower than a quench, but faster than leaving it in the furnace.
Right. This process, called normalizing, essentially resets and refines the steel's internal grain structure.
And this resetting and refining, that's why normalizing is so powerful.
Okay.
It's typically applied to carbon manganese steels and some low alloy steels, and the goal is to optimize both strength and toughness
How does it do that?
by making the tiny crystal grains within the steel smaller and more uniform.
Ah, okay.
It ensures consistent, predictable properties from one piece to another for a given grade of steel. It's all about achieving uniformity and reliability.
Makes sense. Consistency is key in engineering.
Absolutely.
Okay, this next one sounds a bit dramatic, doesn't it? Quenched and tempered steel.
Q&T. Yeah, it does sound intense.
Quenching is heating steel to about 900 degrees C, again, transforming it into that austenite phase, and then cooling it super fast, like dunking it in water or oil.
A very rapid cool that locks in a very hard structure, right?
Incredibly hard, yes, but often brittle because of that hardness.
Right.
So here's the kicker. After that aggressive cool, the steel must be tempered.
Okay, what's tempering?
It's essentially reheating it, but to a lower temperature, maybe 500, 600 degrees C, something like that.
Below the transformation temperature.
Yes. And then slowly cooling it, it softens it just enough, improves its ductility, its toughness, stops it being so brittle.
Got it. So this technique is used for some low alloy steels mainly.
Primarily, yeah.
To achieve very high strength, maybe excellent toughness, or superior wear resistance.
Exactly. The quenching creates a very hard, often brittle structure called martensite.
Martensite, okay. And the tempering cycle then reheats it, lets it soak, air cools it, carefully striking that critical balance between maximum hardness and necessary flexibility.
Making the steel usable in really demanding applications.
Precisely.
Now let's talk about solution annealed, or solution heat-treated steel.
Okay, another specific one.
Yeah, this process is primarily for a very specific family, stainless steels.
Ah, okay. Austenitic stainless steels, mainly.
Mostly, yes, like the common 304 and 316 grades you see everywhere.
So what's the process here?
It involves heating the steel, often after it's been hot or cold, worked to an even higher temperature, typically around 1100 degrees C.
Wow, that's really hot.
It is. And then, crucially, rapidly cooling it by quenching in water.
So another rapid cool. Why is that so critical here for stainless?
It prevents unwanted things called carbides or other distinct phases from forming as it cools.
Okay, phases being different internal arrangements or compounds.
Yeah, different atomic structures within the metal, each with unique properties. And for these stainless steels, this treatment is essential.
To maintain their specific corrosion resistance and mechanical properties?
Exactly. Without it, they just wouldn't perform as expected, especially in corrosive environments. That rapid cool locks in the desired structure.
Got it. Critical for stainless.
Finally, in this section, we have annealed steel.
Annealed, okay.
This is a bit similar to normalizing in that the steel is heated to about 900 degrees C.
Right, into that austenite range again.
But then, instead of air cooling, it's allowed to cool very, very slowly inside the furnace itself, sometimes over many hours or even days.
Super slow cool. What does that do compared to, say, air cooling and normalizing?
What do you think? Slower cooling.
It gives everything more time to settle, maybe makes it softer.
Exactly. That slow, controlled cooling right within the furnace gives the steel's internal structure maximum time to rearrange into its softest, most stable state.
So it intentionally reduces the steel's strength and toughness.
It does, but it significantly improves its ductility, its ability to deform without breaking.
Ah, so it makes it much easier to work with.
Precisely. For things like pressing, bending, or forging operations, it's applied to CMN steels and some low alloy steels, mainly for that workability.
So soft and good for manufacturing.
Pretty much.
Okay, that covers the main starting states. Quite a range of properties from tweaking heat and cooling.
It really is. We've
Yeah.
spent a lot of time on steel's birth certificate, its initial properties.
Yes.
But what happens once we take these carefully treated pieces and join them together? With the intense heat of welding.
Ah, yes. Welding changes things locally, doesn't it?
It sure does. That process can introduce its own set of challenges. Changes the material right around the weld.
Creates stresses, new microstructures.
Exactly. And that's where post-weld heat treatment, or PWHT, becomes absolutely essential in many cases.
Right. PWHT isn't just an optional step sometimes. It's applied to certain welded steels to ensure the properties of the entire weldment.
The original steel and the new weld joint.
Yes, the whole thing
Mhm.
are suitable for its intended application. Safety and performance rely on it.
So what's the temperature range here? Are we transforming it again?
No, generally the temperature for PWHT is typically well below where those major phase changes occur, like forming austenite.
Okay.
Instead, it's high enough, usually around 600, 750 degrees C, depending on the steel, to effectively relieve residual stresses.
Stress is built up from the welding process itself.
Exactly, from the heating and cooling cycle of the weld. And it also softens any hard or brittle regions in what's called the heat-affected zone, or HAZ.
The HAZ. That's the area of the original steel right next to the weld that got heated but didn't melt.
Precisely. It sees a thermal cycle, too, which can harden it undesirably.
So if it's not about changing the fundamental structure like the initial treatments, what does this stress relief truly mean for the steel's performance? Why is it so vital for, say, a pressure vessel or a pipeline?
Well, the major benefits of PWHT are really clear, and they're often about preventing catastrophic failure.
Okay, like what?
First, it drastically improves the joint's resistance to brittle fracture.
Ah, snapping suddenly under stress?
Yes, like glass. PWHT makes the steel much more resilient, less prone to those sudden catastrophic failures. Real nightmare scenarios for engineers.
I can imagine. What else?
Second, it significantly improved the resistance to stress corrosion cracking, or SCC.
Okay, what's that?
That's when tiny cracks grow over time, often in corrosive environments, specifically where there's residual stress pulling things apart at a microscopic level. PWHT removes a lot of that stress.
Big problem in chemical plants or pipelines, I bet.
Huge problem. And third, bit more practical maybe, it allows welded joints to be machined to accurate dimensional tolerances.
Ah, because the stresses are gone, it won't warp when you cut it.
Exactly. Crucial for precision engineering, where every millimeter, or even less, matters.
So because the main benefit is reducing those internal stresses.
People often just call PWHT stress relief. It's pretty much synonymous.
That makes a lot of sense. Huge for precision, ensuring things fit. But, achieving that level of stress relief, that dimensional stability, does that come with challenges? Energy costs. Yeah. Scale of equipment for massive structures.
Oh, absolutely. It's a significant operation.
And how exactly is this stress relief done? It's not just chucking the steel into any old oven, is it?
Definitely not. Just like, baking that complex cake we talked about.
Yeah.
PWHT is a highly controlled process. There's a strict recipe specified by application standards and codes, ASME, EN standards, etc.
A recipe, okay.
And to ensure a PWHT cycle meets those stringent requirements, a detailed procedure must specify 4 critical parameters. It's all about precise control of that thermal cycle.
Okay, so what are these key ingredients in this thermal recipe? Let's start with the heating phase.
Right. First, the maximum heating rate.
Why control how fast you heat it?
It must be very carefully controlled to prevent large temperature differences, what we call thermal gradients, from developing within the fabricated item.
Okay, why are gradients bad?
Because those gradients can produce huge internal stresses all by themselves, leading to distortion or even cracking, especially in complex shapes or thick sections.
Ah, so you could damage it just by heating it too quickly?
Precisely. Application standards typically require controlled heating above about 300 degrees C.
Why 300 C?
Because above that temperature, steel starts losing significant strength and becomes much more susceptible to distortion from those thermal gradients.
And how do they track this? Make sure they're not going too fast.
They use thermocouples, little temperature sensors attached directly to the item's surface.
Taking the steel's temperature in real time.
Yeah, monitoring temperatures constantly to ensure compliance. For common carbon manganese steel, heating rates are usually somewhere between, say, 60 to 200 degrees C per hour. Depends on the thickness.
Quite a delicate balance then, isn't it? Not too fast, not too slow.
It truly is. Okay, the second critical parameter is the soak temperature range.
So the target temperature you hold it at.
Exactly. This is the specific temperature range where the item is held for a period of time. And this temperature depends entirely on the type of steel.
Different steels need different soak temps.
Absolutely. For carbon and CMN steels, it's typically around 580 to 620 degrees C, something like that.
Okay.
But some specialized low-alloy steels, like the chromium molybdenum steels, CR Moss steels, used for high-temperature service in power plants.
Yeah.
They require much higher temperatures, often in the 700 to 760 degrees C range, to get the right stress relief and temper any hard microstructures effectively.
And the soak temperature, it isn't just a guideline, is it? You mentioned it's an essential variable for something called a WPQR.
That's right, a welding procedure qualification record. It's a legally binding document in many industries.
Sounds serious. So if you mess this up, get the temperature wrong.
The consequences can be severe. You might have to redo the entire expensive qualification test for that welding procedure.
Okay.
Or worse, the actual component might not be fit for its intended purpose. It might fail later in service. It's a non-negotiable parameter. You have to hit that specified range.
Got it. Critical stuff. What's the third parameter?
The third is the minimum time at soak temperature, often just called the soak time.
How long you keep it hot.
Exactly. And it's crucial to allow enough time for all the welded joints, especially the thickest sections of the fabrication, to not only reach but also fully experience the specified temperature throughout their entire thickness.
So it's not just the surface getting hot.
No, the heat has to penetrate all the way through. Equalize temperatures. Allow those stresses deep inside the material to relax.
Makes sense. Is there a rule of thumb for how long?
A common one, often specified in codes for CMN steels, is about 1 hour for every 25 millimeter or 1 inch of thickness, based on the thickest part being heat treated.
1 hour per inch. Okay. It's a reminder of just how much precision goes into this. You're literally baking in the resilience that ensures a critical component lasts for decades.
That's a good way to think about it. Baking in the safety and reliability.
Astonishing. And finally, the fourth parameter.
Finally, the maximum cooling rate.
Just like heating, you control the cooling too.
Yes. The cooling rate from the PWHT soak temperature must be controlled. Same reason as heating, really.
To avoid distortion or cracking from thermal gradients again.
Exactly. High stresses can develop during cooling too if one part cools much faster than another. Codes typically specify controlled cooling down to around 300 degrees C again.
And below 300 C.
Below that temperature, the steel has generally regained enough strength that it's unlikely to suffer significant plastic strain or distortion from any remaining temperature gradients.
So you can usually remove it from the furnace then? Let it cool in the open air?
Often, yes. It can just cool naturally in the ambient air below that point.
Okay, so this whole controlled operation, heating, soaking, cooling, it takes place in specialized heat treatment furnaces.
Correct.
I'm picturing a giant industrial oven, but I imagine there are specific considerations, especially if they're oil or gas-fired.
You're right to picture a giant oven, but yeah, with added complexities. It's absolutely critical that flames from oil or gas-fired furnaces do not directly contact the fabrication.
Direct flame impingement. Why is that bad?
It can create localized hotspots, really intense thermal gradients within the steel, which completely negates the precise control we've just spent all this time discussing.
Undermines the whole process.
Totally. Also, the fuel itself, especially for oil-fired furnaces, must have low levels of harmful impurities, like sulfur.
Sulfur? Why is that an issue?
Sulfur can actually diffuse into the steel surface at high temperatures, potentially causing issues like hot cracking or reducing corrosion resistance later on. So low sulfur fuel is often specified.
Wow. Lots to consider even with the furnace fuel. Okay, that makes sense for components you can fit in a furnace. But what about something enormous, like a really long pipeline or a massive pressure vessel that's already assembled out in the field?
Yeah, good question. You obviously can't put the whole thing in a furnace.
So how do you apply PWHT then?
That's where we turn to local PWHT.
Local. Makes sense.
For pipelines, large pipe spools, closing welds on big vessels or other massive field fabrications, It's often necessary and practical to apply PWHT only to individual welds or specific regions.
Heating just the area around the weld?
Exactly. And for this, the procedure needs to specify not just those thermal cycle parameters we've discussed, heating rate, soak temp, soak time, cooling rate, but also the width of the heated band where the soak temperature is actually maintained around the weld.
Okay, the hot zone.
And also the width of the temperature decay band. That's the zone next to the heated band where the temperature gradually and controllably drops back down to around that 300 C mark.
So you need controlled heating and controlled gradients next to the hot zone.
Yes, to manage the stresses induced by the localized heating itself.
So it's about creating a precisely controlled heat zone around just the weld. I assume other things become even more critical then, like exactly where you put the thermocouples within these bands.
Absolutely crucial. Thermocouple placement is key to verifying the soak temperature across the required bandwidth and thickness.
And how the whole thing is supported, because it's going to expand when heated locally.
Yes, proper support is vital to allow for thermal expansion and contraction without introducing new stresses or causing distortion. It needs to be able to move freely.
Okay, so what's the common way to actually heat these localized areas? How do they do it in the field?
The most common method uses insulated electrical resistance heating elements, often flexible ceramic pads containing heating wires, sometimes called electrical mats.
Like electric blankets for steel welds.
Kind of, yeah. They're wrapped directly around the weld area, covered in insulation, and powered by welding machines or specialized PWHT power sources.
Clever.
Gas-fired, high-velocity burners, or radiant heating elements can also be employed, especially for larger or thicker components, creating a precise, contained thermal environment for that specific weld zone.
Fascinating stuff. Lots of ways to apply that controlled heat. So wrapping things up, what does this all mean for you, our listener? We've covered a lot today.
We certainly have.
From the initial birth of steel's properties through those various heat treatments.
Rolled TMCP, normalized Q&T.
Right. To the incredibly precise and critical process of post-weld heat treatment. It seems clear that manipulating temperature and time, it transforms ordinary steel into something, well, truly extraordinary.
Capable of withstanding immense forces, harsh environments. It really is a testament to material science and careful engineering.
If we connect this to the bigger picture, it really highlights how much unseen engineering goes into the structures we rely on every single day.
Absolutely. The precise control of these temperature cycles, the deep understanding of material science, the rigorous adherence to codes and standards.
That's what ensures safety, durability, reliability.
In everything from the cars we drive to the bridges we cross, the buildings we work in, the infrastructure that delivers our energy, it's often a silent guardian, this heat treatment process.
It really is. A dance between heat and material, where every degree and every minute matters. So next time you see a large steel structure, a bridge, a building, a pipeline, you'll know a little more about the hidden journey that steel has taken to become what it is, that journey of precise thermal transformation.
And looking ahead, it kind of prompts us to consider, doesn't it?
Yeah.
In a world that's increasingly reliant on even more advanced materials, how might these fundamental principles of heat treatment continue to evolve?
To meet future demands. For even stronger, lighter, maybe more resilient structures?
Exactly. It's a field that is constantly pushing the boundaries of what's possible with materials through heat, but perhaps that's a deep dive for another day.
Indeed. Food for thought.